Okay, so the purpose of this hour is to review some things that will be on the quiz on Thursday, and then also to recap some of the things that we've been talking about for Chapter 14 with regression. So just to review where we've been doing this for a little while, but I just wanted to review it. When we are going through the route of writing down hypotheses, we write down two hypotheses. We write down our boring hypothesis, the null hypothesis. So that's usually the thing that you hope to disprove. So we write all of our statements as to whether or not we accept or reject this null hypothesis. The alternate hypothesis is the other idea. So that could be, this is what is true if the null hypothesis is false. We labeled them H0 and HA for null and alternate hypothesis. We are often, usually, testing for significance. We can be testing, this is what helps us decide whether or not to accept the null hypothesis and infer that the difference is significantly greater than the chance difference. So we have either a one-tailed test or a two-tailed test that we end up doing. So one-tailed and two-tailed tests all come down to what part of the curve you are looking for. So our either Z distribution or T distribution is a symmetric distribution with a mean right here in the middle of 0. And a one-tailed test means that we are looking to disprove a null hypothesis and say that our data is actually in this area of the region of the curve. So this, if we were looking for a left-tailed, this would be a one-tailed test where we were looking for a left-tailed test. If we were looking up here, then this would be a one-tailed test where we were looking for the right tail of our test. A two-tailed test means that we're going to have rejection regions in either of these two regions. Okay, and if our null hypothesis has a greater than sign, this will end up being a right-tailed test. So if we have a null hypothesis, or an alternate hypothesis or a null hypothesis that has something to the effect of the mean is greater than 25, that greater than sign means that we are looking for something in this area that's to the right of, on the right-hand side of this curve. If we had a mean is less than 25, a less than sign for a left-tailed test, we'd be looking down here. And our two-tailed test would just be that we are looking for the fact that maybe the mean is not equal to 25. And that would allow for a mean less than 25 or greater than 25. I actually want to do this after we do the problem, so I'll come back to this in a second. So here is a review example from Chapter 9, a different version of something that we've done that is similar. So for hypothesis testing when the population mean is unknown. So in our last quiz, we did an example that was similar to this, except that it was a hypothesis test for when the population mean was known. And now we are changing this to be an unknown value. So what I have provided is a sample mean of 28. And this sample mean is based on 32 different samples. We have a sample standard deviation is 7. And the question says I want to use a one mean t-test to perform the required hypothesis test at the 5% significance level. So I've given you the two hypotheses. The null hypothesis is that the mean is equal to 25, and the alternate hypothesis is that the mean is greater than 25. So just to sort of draw what we're looking at here is that we have a situation where we are going to have a t distribution now. So we're going to use the t table instead of the z table to test this, where we say here is the population mean, that this is the population mean is 25. What we do is we take this 25 and we transform this population mean into a t, into the t variable. So this population mean in 25 here also corresponds to a t value of 0. And so the question is 28 actually bigger than 25 with statistical confidence? So certainly 28 is going to be on the right side over here to the right of 25. But the question is 28 to the right of this value right here, and it's in the shaded region? If it is, then we'll be able to reject our null hypothesis. If 28 is to the left of this, then we won't be able to reject our null hypothesis. We will fail to reject the null hypothesis. And the value right here that separates our rejection region from our fail to reject region is this value of t right here, called the critical value of t. The procedure for solving a problem like this is we have to find two different t's. One is going to be that we're going to find the value of the test statistic t. That is that we are going to use this formula here to turn 28 into a t-score using that formula. That will be the answer to C. What's the value of the test statistic? And then the other thing that we're going to do is we're going to use the table to figure out the critical value of the test statistic. So the value of this number that is right here. So that sort of sets up the problem. And now let's do the problem. So what is the value of alpha? I think I have just gotten rid of it. We are trying to find the value of alpha required to test this hypothesis at the 5% significance level. So we are looking for a value of alpha that corresponds to 5% of the area under this curve. So alpha is 0.05 here. For B, is this a right-tailed, a left-tailed, or a two-tailed test? This is a right-tailed test because we are looking for the area under the curve that is to the right of this. So this is a right-tailed test. For C, what is the value of the test statistic? So we're going to use the formula, which is right up here, and plug in the numbers and find out the t-score of this number of 28. So the test statistic t is x bar minus our population mean that we are trying to test, divided by the sample standard deviation over the square root of the number of samples that we have. So this will be 28 minus 25 divided by 7 over the square root of 32. Oh. 28 minus 25 is 3, and then I'll divide that by 7 divided by the square root of 32. And I get 2.42. I don't see it very well. So I got that to be 2.42. Okay, so t is 0, is in the middle of this distribution, and our t is 2.42, somewhere to the right of here. We don't yet know if 2.42 is something that's going to plot to the right of this critical value or to the left of the critical value, because we have not yet found the critical value. So for the critical value of the test statistic, we're going to go to the table, which is here. So for the table, it's a different table than we're used to looking at. So it's the T table instead of the Z table, but I think it's actually easier to look at this table. So the degrees of freedom column we're going to follow down. The degrees of freedom is always the number of samples minus 1 for this table. So we're going to follow this all the way down to 32 minus 1, which is 31. So it will be one of the numbers on this row that I've just circled that's our critical value. And if I follow this up to the top, I am looking for the t-score that corresponds to 5% of the area under the curve. So I'm going to look for the t of 0.05 and follow that all the way down to here. So my critical t is 1.696. So that's the answer to D. So I can now say that this right here is 1.696. That's the critical value. Our test statistic is greater than that number, so it's all the way out here, 2.42. So I have a test statistic that is in the rejection region, so I'm able to reject this null hypothesis. So the question of part E says, are you able to reject it? And I want you to state it in a complete sentence. So I will say that yes, I am able to reject the null hypothesis with 95% confidence. I can safely say that 28 is greater than 25. Okay. So it may not surprise you that a question like this will be one of two questions on your quiz. So it will be a t-test. So you'll use the t-table to answer the question. And it'll be very similar to this. The numbers will change. It will either be a right-tailed test, a left-tailed test, or a two-tailed test. And this will be the wording of the 5 of the sort of of the parts that you need to answer. So that is something to look at and make sure you feel comfortable with. And now I want to go back to another side here. Yep. What we just did to kind of recap. Okay, so steps to do the t-test. We identified our hypothesis and our null hypothesis and our alternate hypothesis. We determined if the test was a left-tailed test, a right-tailed test, or a two-tailed test. The next thing we're going to do is calculate the value of the test statistic using this formula, which I corrected before, but it's x bar minus the population standard deviation, population mean that we're trying to test, divided by the sample standard deviation over the square root of the number of samples. And then we use the table to determine the critical value of the test statistic. I just did one for a right-tailed test. And this is the right-tailed test, what this looks like. So we had a rejection region that was on the right-hand side of this curve. If this was a left-tailed test, where we were looking for something that was less than in our hypotheses, then we would be looking for, we would have found, I'll just even go back to the same number that we were looking at. Here we looked up in the t-table and we found it to be 1.696. If we had been doing a left-tailed test with that, our critical t-value wouldn't have been positive 1.696. It would have been negative 1.696. Otherwise, that would have been the same. If this had been a two-tailed test, then we would have been looking for a different number altogether, because we have 5%, that our alpha value was 5%. And so we have to divide that 5% among the top half of the curve and the bottom half of the curve. So that means that we would actually only be looking for something that corresponds to 2.5% of the area under the curve. So just to kind of show you what I would use on this t-table to make that work, is that now I would be starting here. So my alpha value is still 0.05, but because this would have been a two-tailed test, or I guess I should say if this was a two-tailed test, we would be following the column that only corresponds to alpha over 2 here. And then I would follow this down, all the way down to the same 31, and would find that I had a critical t of a larger number of 2.040. I don't want to confuse too much with that. This is the value that we would have gotten as the critical value of t if the example that we just did was a two-tailed test. The test that we just did, it was a one-tailed test, so we had this smaller critical value. Okay, so we identified the critical values by finding the value in the table that either corresponded to t of alpha or t of alpha over 2, depending on if we were doing a one-tailed test or a two-tailed test. And then the last thing that we needed to do was if the value of the test statistic falls in the rejection region. So if it is sort of in here, or in sort of the shaded areas of the curve, then we were able to reject the null hypothesis. Otherwise, we would fail to reject it. Okay, so from there, that is, I think, probably the last example I will ever do from chapter 9. We have been, in the last week, working on regression. And the beginning of regression is graphing. So do we remember how to graph things? So we have a linear equation, and instead of writing this in a way that might be more familiar to you, which is y equals mx plus b, which is the way usually we learn that formula in algebra class, we're going to write this as y equals b naught x plus b naught plus b1x. So now b naught is the y-intercept, and b1 is the slope. Anytime you have a slope, the sign of this tells you something about the way that the graph looks. So a positive slope looks like that. It slopes up. A negative slope slopes down. And zero slope is just a flat horizontal line. So the second of 2 questions on your quiz this week is going to be a question like this, where I will give you a linear equation written in slope-intercept form. I'll ask you to tell me what the y-intercept and the slope are. I will ask you to determine whether the line slopes up or down. I can't really ask you to do it before graphing, but it should be obvious. And then I'll have you draw 2 graphs, 2 points, at least 2 points, and also draw the line that goes through those 2 points. So here is something written in slope-intercept form. The number that multiplies the x is the slope. So slope is -2, and y-intercept is +3. That's your answer to A. And determine whether the line slopes up or down. A negative slope will slope down. And now we're going to graph 2 points to graph the equation. So I know that this has a slope of -2. So that is that a slope is rise over run. So this tells me how much I go up divided by how much I go to the left or to the right. So I can write this slope of -2 as -2 over 1 or 2 over -1. So here's what that looks like. I need to start with a single point, and I'm going to start with my single point being the y-intercept. I know that this line has a y-intercept of 3. So this line goes through the point 0, 3. That's my first. And now I know that my slope is -2. So I'm going to take this first one right here. It says that I can go in the rise direction of -2 and in the run direction of +1. So that means I can go down 2. So the numerator here tells us how much we go up or down. If this is a positive number, it means you go up. If it's a negative number, you go down. So I'm going to go down 2, and then my run, that's the distance that I'm going to travel in the x direction, 1. So I go down 2 and 1 to the right. So I go down 2 and over 1. There's another point on my graph. I go down 2 and over 1, and I can keep doing this. And all of these will be points on my line. So that's the slope is -2 over 1. I can also write the number -2 as 2 divided by -1. So this is a rise of +2. So that means that I go up 2 and a run of -1. So I go up 2, 2 in the positive direction, and then 1 in the negative direction. And there's what that looks like. So I've drawn way more than 2 points. But I've used at least 2 points to graph the equation, and my line will be the line that goes through all of those points, just like that. All right. I had one other example, and this is not it, that I wanted to do from chapter 14 that had to do with regression, just to remind you what we have used regression for. So real data rarely falls on a perfectly straight line, like the example that we just did. Real data actually falls usually scattered, but sometimes it falls in a scattered way that actually looks like maybe it's very close to a straight line. So here is some data that I have. Following are data on age, an age and the length of a fetus. So we have a bunch of fetuses that have been measured, how old they are in weeks relative to how long they are. So we're going to obtain the correlation coefficient between the age and the length. Certainly babies get bigger as they grow, so these two things should be correlated. And we're also going to hop all the way down here and compute the coefficient of determination. And B and C are wordings of questions that I copied from your homework. So I put these in here so you can kind of get an idea of how these things are worded in your homework and how to interpret that answer. So part B says I want to interpret the value of R. That's R is the correlation coefficient, in terms of the linear relationship between the two variables in question. And for part C, I'm going to discuss the graphical interpretation of the value of R and verify that it's consistent with the graph shown. Okay, so we're going to do this in my calculator. And you may or may not remember how to put these things into a calculator, but we will do it anyway right now, as soon as I can feel like you can see that. Okay, it seems like it's visible. So we're going to do this in our calculator, and if you set up your calculator in class to do correlation coefficients, then you don't need to redo this. But if you did not, and I can't really tell how well this is visible to you, so I'm going to do my best, but I will also use verbal cues, so if you can't see what's going on, you can at least hear what's going on. So if you want to set your calculator up for the first time to do correlation coefficients, you're going to hit second and then 0 to go down to your catalog. And then you need to tell it to go down to D. And my D is the green letter right here above the x to the -1 power. And I type that, and then I'm going to scroll all the way down, and I'm going to turn diagnostic on. So I hit enter twice after I get to the diagnostic on, and it is now done. And now my calculator knows to calculate correlation coefficients when it does regression analysis. That's what that was for. You only have to do that once. You don't have to keep doing it over and over again. So if you've already done it in class, you don't need to redo this. Now we need to put this data into my calculator. So we will go to put it in. I need to clear out what was there before, so I'll clear those by getting rid of that data. And I'm going to put my age data in list 1 and my length data in list 2. So bear with me while I do this. And if you have a calculator, I strongly recommend you doing it at the same time. So I'll do this and give you a chance to do it as well. Okay, so now my data is in my 2 lists. If I needed to scatter plot this, I could. The question doesn't ask for it, but to reproduce the scatter plot, I'm going to go make a stat plot. So I'll type second and the y equals to get to the stat plots. And then let's highlight plot 1. Make sure that it's selected is on, not off. And then it looks like a scatter plot. And it is looking to put list 1 in the x values and list 2 in the y values. Let's make sure that makes sense. Should the age be the thing that is plotted on the x-axis? That should be the independent variable, the thing that determines the other one. And yes, it should. So the age definitely should be the independent variable, so it should go on the x-axis. So I'm going to just keep it how it was. And then I go to my graph, and it plots nothing. And the reason that it plots nothing is because I need to adjust the scale of my zoom. So I'll go to zoom, and what seems to always work is zoom 9 for zoom stat. So I type zoom stat, and there it is, and it looks like I had a graph that showed up because I had a line in my y equals from a previous example. So there's my scatter plot, and it looks just like that scatter plot. If I push on trace, and then I can right and left arrow key, and as I right and left arrow key, it will move from one point to another. So it's saying that right now it's looking at the point 18 and 160, which is 18 and 160. So it's sort of on this one right there. I move one over, and it's on 18 and 164. So you can see how that looks. Okay, so to obtain the correlation coefficient, we need to go to statistics. So we're going to hit the stat button. And then we go over to calculate. And we scroll all the way down to the one that says linear regression, AX plus B. So that's number 8. I hit that, and I hit that again, and it gives me all the data that I could possibly need for this data. So I'm going to go ahead and copy down all of this stuff so I can plot it together. The linear correlation coefficient is R. That's the one that we were asked for. So we'll write that down. That's 0.983. This question should ask how many decimal places I'm looking for. And I didn't say that, so I'll just assume that it's 3 and know how to round it depending on what the question asks for. The coefficient of determination, that's the number r squared. So r squared is 0.966. So this coefficient of determination is the number that says this is the percent of variation that is explained by this linear regression that we just did. So a straight line through this data that we have here, 96.6% of the variation in this data is explained by the straight line that we put through it. So that straight line is a very good fit, in other words. I'll also just copy this down. So it's going to say that y hat, which would be my regression equation. If this question had asked for the regression equation, I would say that y hat is negative 57.773 plus 11.835 times x. So my regression equation would look like that. I'm going to go ahead and plot that just so that we can make sure that it works. So negative 57.773 plus 11.835 times x. And now I'll hit graph to plot it. And this is the line that should go through the data because it is the regression equation that my calculator found to go through the data. And sure enough, it does a really good job of that. Okay. So for B and C, I'm going to write out what the book wrote for the answers to these. And hopefully you can agree that they seem like reasonable answers. So for B, interpret the value of R in terms of the linear relationship between the two variables in question. So basically this question is saying, without doing any statistical significance testing, is this a high correlation? And the answer to that is very much so. This is a very high correlation. Correlation coefficients are always a number between -1 and 1. And the number 1 would be a perfectly straight line where all of the data falls exactly on one line. So this is a very good, a very strong positive linear association between the two variables. It is a very strong positive because the slope is positive, right? This is a positive slope. It's also a positive correlation. If it was a negative slope, we'd have gotten a negative correlation. So there's a very strong positive linear association. I think I am coming off of the screen. Yeah. Between the two variables. Okay, and then for C, part C says, let's discuss the graphical interpretation of the value of R and verify that it's consistent with the graph that's shown. Okay, so we certainly see that the y values are increasing as the x values increase. So a positive correlation is certainly consistent with this graph. We also can see that the data are really tightly clustered around this regression line that we found. So that's the sort of thing that I would expect you to be able to discuss when you're talking about how this graph is related to the value of R. The wording from your book, and on these sorts of answers with your book, they always have those drop-down menus, so sort of most of these words will already be filled in, and it'll be up to you to fill in the last of the words. So the book's answer to this was that the graph is consistent with what we said in B. So the graph the reason it's consistent is because the y values increase as the x values increase. And the data are clustered closely about the regression line. Okay, so hopefully you feel we are done talking about new, and there's one more homework assignment on all of this regression stuff that is due in about a week. And yeah, it feels like the end of the semester. There's not many things left to cover. So hopefully I will see you in class and see how, and you will do very well on the quiz.